Good morning. All right, so we're going to start with the dimension of a vector space today. So we're looking at section 4.5 in our text. And we're going to start with a couple of theorems and move into some definitions. And I think most of this is fairly straightforward, but we'll find out. So let's start with theorem 9. So we're looking at theorem 9, and it's saying that the vector space that we're looking at has n vectors. So we're saying that the vector space has a basis of n vectors. What we're saying is that any set in V, so any set that's in V containing more than n vectors, has to have a dependency built in. And that's sort of cooked into or baked into this definition of our basis. Remember, as you recall, that a basis has to be the most efficient spanning set that we're looking at. What this is saying is that if the set has any more than n vectors in it, then obviously a dependency would have to be built in. So that seems fairly straightforward. What does theorem 10 then tell us? It says that if a vector space V has a basis of n vectors, then every basis, every single one, has to have exactly n vectors. And again, that makes sense that if we have something that's defined as the most efficient spanning set, then by definition of most, there is not going to be allowed to be a basis that maybe has a different number of vectors. Otherwise, that most isn't necessarily well applied. So Theorem 10 is pretty straightforward based on what we know about a basis. Now, this next definition is sort of interesting. It says that if V is spanned by a finite set, then V is said to be finite dimensional, which is probably not so interesting and probably expected. And the dimension of V is often just written, this is just a notational piece here, that we're describing the dimension of V as dim V, is the number of vectors in the basis for V. Now, the dimension of the zero vector space is defined to be 0. I would say that this is a little counterintuitive in the sense that there is one vector needed to generate the zero vector, but I think that what we're looking at oftentimes is trying to determine whether the dimensionality lines up with the number of unique vectors that it needs to create. So the vector space of the zero vector is defined to have a dimension of 0. Now, this last sentence feels like it's a little bit of a throwaway sentence, but to be honest, if you're going to stare at this long enough, I think you might have trouble, envisioning what this is getting at. But if V is not spanned by a finite set, so if for some reason in order to generate V we need something more than a finite set, then V is said to be infinite dimensional. So what are we talking about if we're talking about something that is infinite dimensional? Well, let's consider just, something that maybe we don't have a ton of experience with, but let's consider the vector space of, say, all polynomials that span over the real numbers. So if we're talking about the set of polynomial functions, this is a vector space, but it's not generated by a finite set. Meaning, let's think about what the functions would look like. So f of n based off of some input x is defined as x to the n. So we're looking at any polynomial. Obviously, the dimension of this is infinite. So if we're looking at this, and clearly, obviously, the zero vector is a member of this set. So we know that this is, in fact, a vector space, but we also know that it would take more than a finite number of vectors in order to generate all polynomials of all degrees. So we're looking at something that would be referred to as infinite dimensional. Okay, so let's look maybe a more straightforward or a much smaller example. So the standard basis for the degree 3 polynomials. So the standard basis obviously would look something like this. And we would say that would be the standard dimension. Now, the interesting piece here is that if we're looking at the standard basis for all degree 3 polynomials, obviously that dimension is 4. Now, if we contrast that with, say, the standard basis for Rn standard basis is just, in fact, those standard vectors e1 through en, where those are the columns of the identity matrix of dimensionality n. So, for example, the dimension of R3 is just 3. Now, the reason why this is noteworthy is obviously these are not the same. So one thing that we want to make sure that is sort of clear in general is that the dimension of, say, any polynomial vector space, degree n, is in fact always going to be n plus 1, but the dimension of any real number space is always going to just be n. So I want to make sure that that contrast is sort of illustrated there. Let's look at a little bit more of a unique example. Find a basis in the dimension of the following subspace. So they're telling us that this is a subspace. Let's examine this a little bit more carefully. Obviously, we can break this apart and say, let's look at this in its components. So we could define this as 1, 2, 0, 3. B then scaled with 1, 2, 1, 0. C when scaled with 2, 4, 1, 3. And then obviously D when scaled with 0, 1, 1, 1. Now when we look at this unique set of vectors, and we can call each of these, V1, V2, V3, and V4. If we look at this unique set of vectors, we obviously recognize that W is equal to the span of V1, V2, V3, and V4. But is that the most efficient set that we could use to define W? And I would argue that, if we look at this just not too long, we look at V3 being 2, 4, 1, 3, and we recognize that V1 is being 1, 2, 0, 3, and V2 being 1, 2, 1, 0. V3 is clearly a linear combination of V1 and V2. Now, it does go to just quickly check that V4 is not a linear combination of any of the three previous vectors. So the most efficient basis we could generate, the basis, let's get off this highlighter for a second. The basis for W obviously would be V1, V2, and V4, which would mean that the dimension of W is in fact just 3, which we can now verify that by simply looking at the independency of those three vectors. Okay, so let's do some just quick hitting examples. So obviously, as we talked about, the zero-dimensional subspace containing only the 0 vector is going to have a dimension of 0. So the dimension of that subspace is going to be 0. Maybe a little counterintuitive, but it is a fact we're going to have to establish or accept. The one-dimensional subspaces are clearly going to simply be the span of a unique vector where that vector is non-zero. And these subspaces, when we're talking about them in R3, are a line through the origin. And the reason why they have to travel through the origin is that in order to be defined as a subspace, the 0 vector has to be included. The two-dimensional subspaces, obviously, if we span two unique vectors, so we're looking at spanning U and V, where U and V are in R3 and are not necessarily multiples of each other. That's why we're talking about them as being two-dimensional. These subspaces obviously create a plane through the origin, which we've talked about in the past. And again, the reason why we can say that it has to travel through the origin is because of the qualifier subspace. Obviously, we're looking at a three-dimensional subspace. We're looking at a span of three unique vectors in R3 that have to be linearly independent. So we're looking at three vectors in R3, then this subspace in R3. The subspace is R3 itself because the columns of A, which would be these three vectors, do span all of R3. All right. Last theorem here, and then we'll get into maybe hopefully some more interesting examples. Let H be a subspace of a finite dimensional vector space V. So we're saying that we have some finite dimensional vector space V, and we're looking at a subspace of that. Any linearly independent set in H can be expanded. So we're looking at a set of independent vectors in H. That set can be expanded to generate a basis for H. And all this is saying is that if we know that V is a vector space, and then it's finite, it can be spanned by a finite set of vectors, then if H is a subspace of that, then we can expand the set of independent vectors in H to generate a basis for H. All it's saying is that if we have a basis for V, then there has to be a basis for H. Also, H is finite dimensional, but the dimension of H is always going to be less than or equal to the dimension of V, which makes sense because it is a subspace. Okay, so let's take a quick look at this. What is this talking about then? So we're looking at, say, let H be the span of these two vectors, 1, 0, 0, and 1, 1, 0. Then H is obviously a subspace of R3 based on the number of entries in each of those column vectors. And obviously the dimension of H is less than the dimension of R3. Obviously the dimension of R3 would be 3, but clearly the dimension of H is simply 2 because it only has two vectors in its span, and those two vectors are independent. We could expand this set to include, say, 0, 1, 1. This would allow us to form a basis for R3, and now all we're simply saying is that we could take these three vectors, which originally were the first two, and add a third to generate a basis for R3. Okay, So then what is this saying then in terms of theorem 12? We're looking at this as the basis theorem. We're saying that if V is p-dimensional, so we're defining the dimension of the vector space as p, and it's greater than or equal to 1, then any linearly independent set of exactly p vectors in V is automatically a basis for V. And again, this sort of makes sense in terms of our definition for basis. We know that basis is the most efficient spanning set for a given vector space. And so if we're looking at the dimension of the vector space being defined as p, then that has to be the number of vectors in our basis. And so this feels like it's very intuitive. Now, what does this look like in terms of an example? We're going to say, let's show that this particular set, t1 minus t, 1 plus t minus t squared, is a basis for all degree 2 polynomials. Well, how would we go about doing this? Well, let's consider 3 vectors then in place of these 3 pieces in this particular basis that is to be shown. So we can define V1 as, say, 0, 1, 0. We can define V2 as 1, negative 1, 0. And we can define V3 as 1, 1, negative 1. Now let's take these 3 vectors and let's consider them as one 3 by 3 matrices. And let's without any uniqueness here, we're just going to define this as A. What would the reduced row echelon form of A give us? So if we're looking at reducing this, well, the uniqueness here is that, or the unique idea is that it ends up spitting out exactly the identity matrix. Now, what does that tell us? It tells us that we have 3 independent columns here. Thus, we have 3 independent vectors. So yes, obviously, these 3 vectors would form a basis for P2. So V1, V2, V3 obviously would form a basis. The basis of P2 could be defined as those 3 vectors. Thus, the dimension of P2 has to be 3 based on what we're looking at here. So we've shown that this is, in fact, a basis by saying that we know that there are 3 vectors that generate this particular set. Okay, so let's continue to think through this then. So the dimension of P2 is 3. We know that there are 3 vectors in this basis. So according to the previous theorem, we know that, in fact, these 3 vectors would be a basis because the number of vectors it takes to create the basis is the same as the dimension of P2 itself. Okay, so let's look at another example of using dimension or establishing dimension. Let's suppose that A is given as the following, and let's find the dimension of the column space of A and the dimension of the null space of A. So the first thing that I would ask us to consider is, what would we have if we reduce A? So let's reduce A, and we would say that that will give us 1, 2, 3, 4. So throw this into your machine to verify, and then 0, 0, 1, 0. Now what I'm seeing here clearly is that we're looking at two columns here where we're looking at, we have we have 2 free variables, but we have 2 independent vectors in the column space. So the column space of A is defined by these 2 vectors, 1, 2, and 3, 7. So obviously the dimension of the column space, whoops, my pen's not happy right now. The dimension of the column space of A is clearly just 2. But the fact that we have 2 free variables means that the dimension of our null space is also 2. And so what we're looking at there, I'm not sure why I've got so much blue over here, but just wanted to clean this up. So what we're looking at here is that we can clearly find the dimension of our column space and the dimension of our null space by examining the reduced row and looking at the number of free variables versus the number of pivot positions. So this is something that I would like to just summarize here. Make sure that we pay attention to this. This will probably be something that'll be quickly established for us. But the dimension of the null space of A is simply the number of free variables of A, whereas the dimension of the column space of A is simply the number of pivot columns of A. All right, so I hope that helped to kind of talk about the dimensions of a vector space. Obviously, you have questions.